My name is Neil Barrett, and so today we're going to do a quick, hopefully around 30-minute talk and show around what Fred's capabilities are for Straylight. For those of you that are new to Fred, first of all, just a very quick overview about what is Fred. Fred is a comprehensive optomechanical ray tracing software package that can be used to solve a vast number of different problems. Straylight analysis is the topic for today and is also the thing that Fred is actually used very often for. But we can also use Fred to solve different problems, propagate coherent beams, analyze imaging systems, illumination, thermal, infrared optics. We can do some tolerancing, we can optimize. So Fred is capable for a lot of different things, but today we're going to focus on Straylight. So we only have 30 minutes here, so it's going to be a pretty quick run through about some interesting tools that we can use, and then a demo of actually using those tools within Fred to show you kind of how to use them and get the benefits of those tools. So Straylight, first of all, what is it? Straylight is unwanted light in your optical system, and that can come from different sources. It can come from specular ghosts. That's light that reflects from transmissive surfaces. It can come from scattering. The scattering can be on the optical surfaces. It can be on any other surface too. Optical systems can have dust or particulates that actually scatter light. Diffraction effects can also cause light to be present in places that we don't expect. So things like diffraction from apertures. When we actually manufacture optics, especially for things like diamond turned optics, we can leave grooves in them, which lead to actually grating type effects that also cause light to scatter into regions we wouldn't expect. In the infrared, we can also have thermal self-emission, where the actual detector images itself. And then, of course, we have the usual thing about having bright light sources just outside the field of view, and also scattering from the glass as well. So there's lots of different places that this stray light can actually come from. So in terms of the tools that Fred has for us to model this, the first great thing that Fred has is an abundance of different scatter models. So Fred has lots of different models for us to choose from, and of course we need to pick the one that best represents the type of scattering that we expect to see. So we have all the usual suspects of Lambertian scattering, Harvey, Shack, but we also have a number of different other models as well. So we can model scattering from essentially particulates. We also have some polynomial scatter models, which are very useful for fitting measured data too. And if push comes to shove and none of the other 12 models work for us, we always have the option of a user scripted scattering, where we can essentially write any mathematical function that we choose to model our scatter. In addition to being able to model different types of scatter, Fred is also exceptionally good at efficiently modeling scatter. So importance sampling is something that's used in Fred to make sure that the rays that are scattered go towards regions of interest. And Fred offers 6 different ways of doing this. In other software, you might only see one, but Fred has 6 different ways of doing this. So there's a number of different options to spread light in an angle around some definition. So around a specular ray, around some given point in space, or around a given direction in space. And then there's some other options as well, so we can scatter light towards an entity. So any geometry we've previously defined within Fred, we can use that as a target to actually scatter rays to. Also, the option of defining curves in space and scattering to those curves. Now, this option is the one I'm going to use in the demonstration that follows, because scattering through a closed curve is one of the most efficient ways of handling scatter within Fred. And then the final option is scattering through some volume, so we can define a sphere or an ellipse and scatter through that too. So the importance sampling is of course critical. But the other feature that Fred has that makes it quite suitable for Straylight is the fact that we can mix and match scatter functions and importance sampling definitions as well. So we can have more than one scatter model and more than one importance sampling definition applied to a surface. So this screenshot here has a Harvey-Shack model for a polished surface, but also has particulate me scatter model applied as well for particles of a 400 micron size. And then in terms of directions to scatter to, we can pick different directions as well and encourage light to go in places which are interesting for us. And then one of the really big things that Fred has, which makes it really great for Straylight and just ray tracing in general, is the fact that Fred has Raytrace Properties. So rather than being forced at a global level to define whether rays split or not, or scatter or not, within Fred, we can actually choose to define different rules about whether light can split or scatter, and we can apply those rules on a surface by surface basis. So this gives us granular control about what types of interactions are going to be allowed within our model. And as I said, these controls, the critical thing is that we can apply them on an individual surface level. So we can allow one surface to scatter, another one to not. This surface might scatter in transmission only, another surface might scatter within reflection, and we can mix and match. And essentially, another thing that we can use this for as well is we could actually define different ray trace properties to allow higher degrees of scatter the further into an optical system we go. So the closer we are to maybe an image plane, and we could actually allow the rays to scatter more. And then one of the other things that Fred has is, which really helps it for Straylight problems, is that it has a user interface that has been optimized and designed to work really well for optomechanics. So the user interface itself is designed from the ground up to make it very easy to set and also keep track of all of the optics, mechanics, and various surface finishes, the coatings, etc., in really large models as well. So we have a CAD object tree definition, and that allows us to conveniently group optics in folders or mechanics. So we can actually group them in either assemblies or sub-assemblies. It's very simple for us to define and refine optical properties applied to our optical model. Keywords are a really great part of Fred that we're going to use here. We're going to demonstrate them being used here, which allow us to have arbitrary complex groupings. So essentially these keywords act as tags. And then the isolation feature that Fred has as well, especially in working in a very complex model, allows us to very quickly focus on parts of the model that are very interesting to us and just remove some of the extra detail whilst we're actually doing that, so we can focus on objects of interest. So that enables us to essentially specify the model and work very easily with the model. Once the ray tracing is done, we also have some very nice tools to analyze what's happened within our optical simulation. So the Raypath and Straylight reports are specialized reports that help us to keep track of all of our rays, the intersection paths they took, the objects they hit, whether they were split, whether they were scattered. And essentially we can report on various different bits of data which are very interesting to us, and we can extract all of the information that we need. From those two reports, we can also extract paths, and we can redraw those paths in the 3D view. So as shown here in this screenshot, a path has been redrawn that shows a ghost between a couple of different lenses. Okay, so we're now going to switch to Fred and show some of these things being used. And for those of you that are new to Fred especially, we do have a Q&A session at the end. So if any questions pop into your mind here from what we're about to do, there is a little text box that you can post some questions in that chat, okay? So we're going to switch to Fred. So I have a start file here, and this start file is of a Heliar objective lens that was imported from a lens design software. A HELIAR is very much like a Cook triplet in that it has a positive element at the front, a positive element at the rear, and a negative element in the middle. The difference between a HELIAR and a Cook triplet is the fact that these positive outer lenses are doublet lenses rather than singlets. So in terms of the CAD tree, in the object tree here, we can see that we have a folder for object sources. In this folder, I have a couple of different fields, which are the imaging path that have been turned off. And in their place, I've added a solar source here, which is going to model light from outside of the field of view. In the next folder down is the geometry folder, and this is expanded here, and I can see I have a couple of different folders. So I have an assembly for the optics, and then also one for the mechanics, and another folder here for the importance sampling targets. So the optics folder is, of course, where we've defined our optics, and if I expand this out further, then we can see that in here are groups of lenses. There's the middle lens here, and also defined here is the image plane. Okay, and if I want to isolate these, I can just right-click and choose to isolate and fit view. The shortcut for that is Alt-X, which I use quite a lot. So if I just choose the shortcut here, this is the contents of the optics folder. And if I switch to the mechanics and do the same again, that's the mechanics. Okay, so it's very easy to switch between views of what is interesting at any given time. So if I go back to the optics here, just expand this out. These optics have already had some keywords defined. So keywords live in their own little folder at the bottom of the tree here. So there's a couple of them in here. But I've essentially already tagged the surfaces of interest just to speed up this demo to try and keep it to around 30 minutes. So surface 1, which is the front surface of the lens, has a keyword that for outer lens surface, as does surface 9. So the front and back surfaces of this lens are tagged with a keyword. And then the interior surfaces as well, these 4 surfaces in the middle, these surfaces are also tagged. Okay, so there's another keyword called inner lens surface. Okay. The mechanics folder, just to expand that and concentrate on this for a second, the mechanics folder is essentially where we house the structure that's going to hold our lens. These are all made from Fred native parts. They could be CAD parts. We could have imported some CAD models for this, but I just thought I'd show that we can do this with native parts as well. There's an outer barrel which actually is turned off. That's because this original outer barrel, which was the entire length, I actually split it into 2 parts. And the reason I split it into 2 parts is to deal with importance sampling later on. But essentially what we have is a barrel on the outside and some annular structures to hold our lenses in place. Okay, so that's what we have there. And then finally, in the analysis surface folders, we have an analysis surface, which is looking at the rays that end up on the image plane surface. Okay, so this analysis surface is looking at what happens to the rays on the image surface, which is the image plane. Okay, so that's the basic model. To study stray light, we need to think about light reflecting from different surfaces and scattering. So to think about reflections and ghosts, first of all, we need some coatings. In the coatings folder, in addition to the usual 5 coatings that we get with every Fred file by default, I've added 2 further ones here as well. So one is an anti-reflection coating, which is a quarter wave coating. So very, very simple to actually define this, just the wavelengths, the design angle, and the actual substance that the coating is made from. And then this other coating here is this B-bar, which is a broadband anti-reflection coating, which is a 3-layer coating. So quarter wave, half wave, another quarter wave of these materials here. Okay, so 2 different coatings applied. So in terms of how we apply coatings, so the first thing is we can drag and drop optical properties onto surfaces. So actually what I want to do is I want to coat the outer surfaces of the lens. If I just go back to the entire model, I want to coat the outer surfaces of our lenses in the B-bar coating and the inner surfaces with AR. Now I could drag and drop these onto the individual lens surfaces if I want to, but I don't have to because I've already got these keywords in place. So these keywords are really quite useful in that once I've applied keywords to surfaces, I can then apply optical properties via those keywords. So instead of applying them directly to the optics here, I can go to the keywords and I can say that the B-bar coating, I just drag and drop that onto the outer lens surfaces. And you'll see that there are two surfaces are assigned here, printed to the output window. And if I do the same again with the AR coating, drag and drop that onto the inner, then another 4 surface coatings have been applied. So that's the surface that's essentially coated. So it makes it very easy to manage and change these coatings without having to go back and do lots of individual surfaces. So that's the coatings part. We also have the scattering part that we need to model in our Straylight system. So in terms of the scattering, we can define different scatter models. These all live in the scattering folder. So scatterers, again, these 3 scatter functions are defaults that are made with every Fred file. But we've added a 4th in here, which is black anodized aluminium. And this actually is taken from Eric Vest's book on Straylight analysis and control. So this is defined using a diffuse polynomial scatter model. So this is measured data fitted to a mathematical function. And the benefit of doing that is that, first of all, the actual amount of data we need to move around is smaller. It's only nearly 30 lines of data rather than a huge BSDF file. But also in terms of the ray trace, once this mathematical function is set, it's very easy to look up what the BSDF data is for various rays incident on this surface. Within each scatter model, we can choose to apply scattering only on reflection, on transmission, or both. We also have an option here to halt the incident specular ray. In this case, we're not going to halt that incident specular ray. We want it to basically carry on bouncing around and causing other sources of scattered light. The scatter functions, there are lots of them. We add them very simply from the new scatterer, and there's, like I say, there's lots of different choices in here. That was on the slide earlier about all the different choices we have. But once we've defined our scattering, we also have lots of different options to plot them. So from the right click option, there's a bunch of different things here. We can plot scattering as a function of angle. So we can see how the scattering essentially gets worse as we go towards higher angles of incidence. But the scattering itself is very broad. Okay, so not very specular, but quite broad, quite a diffuse scatter. So what we need to do is essentially apply this scatter model to our mechanics. So again, we could just drag and drop this onto the mechanics. And however, I need to change our mechanics in a couple of different ways. So I'm going to do it a slightly different way. The mechanics themselves, by default, when we make them, if I just hover my mouse over one of the surfaces here, we can see that the coating is absorbed and the Raytrace properties halt all. So by default, any mechanics in Fred just stops rays unless we tell it to do something different. So we need to tell Fred to scatter light, which means we need to apply the scatter model, but we also need to apply a sensible ray trace control. And there's also a ray trace control defined in this model. So if I go to the Raytrace properties here, there's a ray trace control called mechanical scatter. Okay, so again, ray trace properties are very useful. These define the rules of what is allowed. So this ray trace property essentially only allows reflected rays, but the reflected ray can be specular or scattered. It also defines some thresholds. So the ray can bounce around a certain number of times and then we stop tracing. And that limits the size of the optical problem. If we didn't have any limits whatsoever, we'd end up with an infinite number of rays that would take an infinite amount of time to trace. So we have to define some thresholds to stop generating rays at. And that's what's controlled here. So we need to apply both the scatter model and the ray trace control to the mechanics, but we also need to do something else. Okay, if I go back to the scatter model here and plot it, you'll see that Fred tells me what the total integrated scatter is. So, angles around 30 degrees degrees, which is the incident angle of our outer field source. The total integrated scatter is around 18%. So around 82% of the light remains specular. And so we need to be aware of that because we want to keep that specular light in our ray trace as well. So we also need to make sure that our mechanics doesn't have this absorb coating on it, because that absorb coating essentially gets rid of all of these specular rays. So actually what we need to do on the mechanics is apply a couple of things. We need to say to the mechanics that we want it to use this scatter model. So I'm just control and click this scatter model with this ray trace property, and the specular ray gets to keep all of its energy. So we'll choose this reflect coating, which doesn't reduce any of the specular ray energy with any absorption or anything like that. Fred will take out the scattered energy first, and what's left over will all go into the specular ray, is what essentially this means. So those are the four things we choose. And then if I just right click, I have the option of applying them all in one go. So we can drag and drop, but we can also select multiple items and apply them to our model in one click. Okay. So the important sampling is next. So this gives some scattering. If I just go back to my mechanics and open one of these items up here, one of these surfaces, in the scatter tab, this will tell me I have the scatter model I wanted, which is good. I have the ray trace the actual ray trace control and the coating that I wanted, which is good. But I also have to be concerned about where the rays are being scattered to. And this is this lower part of the box here on the scatter tab. So this is default scattering. But, default scattering in Fred essentially means that light is allowed to scatter in a hemisphere from the surface normal. So the light can pretty much go anywhere. And ideally, we want the light to kind of go towards the image plane. So we're going to set up important sampling to do this. So there's lots of options here. These are the 6 options I was talking about earlier in terms of how we can direct light in certain ways. So we're in this demonstration, what I'm actually going to do is I'm going to define a default scatter model that isn't a hemisphere, but is instead scatter around specular. So around a 30-degree angle around our specular ray. And I also want to, if you think about the source here, the source is going to direct rays into the entrance aperture of our lens. And really, I want the light that scatters in this front region to go through this opening, and then the light that scatters in the rear region to go through the opening at the end of the optical system, okay? So this is where the important sampling targets come into play. So in the important sampling area, I've actually defined 2 curves. And if I just isolate those, you can see that they're really very simple. Just 2 curves, one in the middle of the optical system and one at the end. And we're going to use these curves to define some rules, or to define some important sampling that says that the surfaces at the front of the optical system here that can essentially see this aperture or this opening will preferentially scatter rays into this opening. And similarly, in the second half of the optical system, the surfaces that face this opening will also scatter light preferentially through that opening. Okay, so those are the 2 targets that we're going to choose, and anything other than that is just going to be around specular. Okay, so let's apply these things. So again, I've already got a keyword defined here for tagging surfaces that are going to scatter towards this middle aperture, this first item in here. Let's put everything back in place. So what I actually want to do, first of all, is just define everything in my mechanical model to be around specular. So I'm going to essentially say the default choice is going to be around specular. So I'm just going to drag that keyword, drag and drop it onto the entire mechanics folder, and you'll see this keyword now pops up. Okay. But then what I want to do is the surfaces in this front half of the system that are facing this aperture, I actually want to change their keyword, this other one, which is towards the mid aperture. So those surfaces are the inner and front of the first ring, the inner and front of the second ring, and the inner of the first part of the barrel. So these surfaces here, I actually want to tag with the keyword towards mid aperture. So I'm going to assign that. You can see you can have more than one keyword against a surface. Okay, so now I have two keywords on these surfaces. So I'm actually going to do now is select that keyword again, just to deselect it, and then click the around specular, and then I can choose the option to unassign keywords. So now I just have one keyword, which is towards mid aperture. That's the first part of the system done. The second part of the system is very similar. I need to define another keyword here actually, so let's do that. So added a new keyword, give it a name, towards exit aperture. And this keyword I want to assign to the surfaces facing the this exit of the rear part of the system. So that is lens to inner and front. So those two surfaces are highlighted there. And then the inner and front face of lens 3, and similarly this one. And also the outer barrel inner face as well. So those 7 surfaces are visible from essentially this kind of curve over here. Okay, so those ones as well, I'm going to do the same trick again, assign the keyword I want, and then get rid of the keyword that I didn't want, because that was just a default that we started with. So now I have all of my surfaces tagged with the actual keywords that I need to apply the scatter definitions that I want in terms of choosing directions in space. So there's a lot of surfaces here. What we don't want to do is kind of go and click through each one of them on an individual level and change what the important sampling specifications are. So when you have a lot of surfaces to edit in bulk like this, the best thing to do is actually to create a little script. So again, I have a little script already prepared here. And this script is a very simple little loop. All it does is it finds the keywords that I'm interested in, which are these keywords for around specular towards mid aperture and towards exit aperture. And there's a little loop that looks through all of the surfaces in my model. If it has one of these keywords applied to it, then it removes any default to start with. And then depending on the keyword it found, so a bunch of if statements here, if the keyword it found is the first one, which is around specular, then it changes the important sampling to around specular with some angle and some number of rays, which are set as variables further up. Similarly, if it finds a different keyword, like towards the mid aperture, it then defines a different set of important sampling. So this is a very short piece of script, less than 40 lines. So very easy to write, very easy to do, but it's a lot simpler than trying to apply important sampling definitions to hundreds of surfaces. So if I just run that script and then go back to the mechanics and take a look, we can see if I just take a look at this surface here, which is around specular. If I open it up in the scatter tab, I have a new scatter direction region of interest or important sample called around specular. And this is at 30 degrees of scatter angle around wherever the specular ray was headed. Similarly, if I go and look at one of the inner or front faces, which are towards our curves, in the scatter tab here, I can see this has a different definition of towards mid aperture, and it's directed scatter rays through a closed curve. Okay, so very quick way of setting these things up. So the scripts, everything's now in place. All we need to do is essentially trace rays and then look at the output. So in terms of tracing rays, we go to the advanced ray trace. And for Straylight analysis in particular, we want Fred to calculate what the paths are, what the actual ray paths are, that groups rays by a common order of surface interactions. Create the ray history file, which enables us to save actual coordinates of where our rays went, so we can redraw them later. And we just run that ray trace. Now this ray trace takes around 8 minutes or so on my laptop here, so I'm not going to try and tell jokes for the next eight minutes whilst that happens. Instead, I'm going to switch to a file that we've already kind of run this analysis on. Okay, so this is the kind of end point. After the analysis runs, we can go to analysis and calculate an arranged and spread function. I already have one open here. So this is the scattered light from the output of our optical system. So this is on a normal linear scale. For Straylight problems, it's often beneficial to change the scale here and look at them at some kind of log scale. So we can do that. We can see there, this is essentially what the Straylight looks like. And we've got these two bright bands, okay? If we go to the tools area and reports, this is where we find the Raytrace paths and the Straylight report that I spoke about on an earlier slide. Okay, these are the two reports that really help us identify kind of what's going on. Take a look at the Raytrace path one first, for instance. This then will populate all the different paths it found, and you can see there are lots of paths, nearly 3 million of them, over 3 million of them, okay? But most of the paths with lots of energy are near the top here. And we can redraw any of these paths by just right-clicking and choosing to redraw a certain path. Or we can take a look at the path details or the path summaries, which will print out the order of interactions. So if I look at path one, for instance, and say, let's look at the path details, then in the output window down the bottom here, it basically tells me what kind of happened. The ray started, and these are all specular kind of interactions with various faces, okay, various surfaces. Okay, so in terms of finding out what paths are causing problems for us, looking through the Raytrace report is interesting, but actually the most helpful thing to do instead is to use the image artifact diagnostic tool. Essentially what we can do here is we can draw a little box around a region of interest. So let's choose this bottom end of this kind of artifact. And now what Fred is doing, and you might not be able to see this, but in the bottom of, oops, here, Fred is looking through the paths. So it's looking through 52 million paths to find out which paths contributed to that small region that I just highlighted. Okay, and this will take Fred a little time, of course, because there's millions and millions of rays, and also nearly 4 million paths. So there's a lot of rays to look through here. 52 million rays split over around 3.6 million paths. Okay, so there's a lot of data to sift through. But when Fred gets to the end of this process, it will be able to tell me which of the various paths contributed to that region. So it's nearly finished here. Let's give it a few more seconds. Okay, so Fred found all of these different paths, and the top paths that's contributed here are path 10 and path 199. Those are the top two contributions in terms of power. So we can, in the Raytrace path summary here, we can right click on path 10 and say, well, let's redraw every fifth ray. There are nearly 2,000 rays in that path. Let's draw every fifth ray. And again, Fred now has to go and look through the 52 million rays to identify these rays and pull them out and draw them in our 3D view. So this will take a little time, but essentially in the 3D view, we'll then see what rays contributed to this region in terms of drawing them and seeing what surfaces they interacted with and how. So this is a really critical tool in terms of understanding how rays are contributing to stray light in certain regions of your image plane. There we go. So it said it's redrawn now. So if I look on my 3D view, this is the path that generates that that little U shape. So you can see the actual distribution of the rays on the image plane, and you can see that essentially all of them come from a specular reflection inside of this ring that's holding this lens in place, this kind of middle lens in place. Okay. So that is the end of the demo. It was a bit of a whirlwind tour of kind of some of the functionality that we have in Fred. For those of you that want further help or further kind of information, then of course the website we have, please go to that and take a look, take a little look around. On the blogs page of our website, we have some articles specifically around Straylight. And of course, you can email us as well. For those of you that are new to Fred, obviously this was a whirlwind intro to some of the things that we can do. We have a 3-day training course coming up, I believe, in September, where we go into a lot of detail around these topics and other topics as well that are basically critical to get the best out of Fred. And I believe we still have seats available on those courses. So if you're interested in those, just let us know. But otherwise, I will turn it over to the Q&A. I think we have a couple of questions. Question from Martin here. How does Fred deal with scatter with a scatter vector? Well, in terms of the other models that Fred has, it's kind of statistically unlikely for the scattered ray to take the exact same path as the specular ray, to the point that it almost virtually never happens. So in terms of the energy calculations overall, it doesn't have that big of an impact, generally speaking. If you have measured data for BSDF, then my understanding is the measurement scheme of that data should take out the specular component. So the actual BSDF data you have for any measured data essentially skips over the specular ray, and you'll see that in the BSDF data sets. When you have an angle of incidence of say 30, the specular reflection data point for 30 will be missing. It'll be there for 29 and there for 31, and I believe we then would interpolate between those two data points. So yeah, you have to remove the specular ray from the BSDF scattered measured data. So hopefully that answers your question, Martin. If not, feel free to contact me after the webinar. Any further questions?
Neil, we actually had someone email in a question as well.
Okay.
So someone asked, what's the difference between coatings and ray trace controls, and why do you need both?
Oh, okay. So ray trace controls and coatings are different in that the Raytrace properties define what is allowed to happen at an individual surface. So whether light is allowed to reflect or transmit or scatter or not. But this doesn't determine how much power those rays have. It only determines whether they're allowed to actually carry on to trace. So once we've allowed as a specular reflected ray, we have to then decide what power that ray has. And it's the coatings that tell us how much power that ray has. So in this very simple demo here, we said we had 100% reflective coating, which essentially means that the specular ray has all the power that it should have after the energy for scattering has been taken out, but there's no further absorption. Hopefully that answers that question.
Excellent. And also, Neil, did you want to let the attendees know about what version of Fred they would need to be able, that you just showed in this demo, what version of Fred they would need to also be able to utilize all these features?
Yeah, sure. So all of the features that I've used in that demo are all in Fred standard. Fred Standard actually has most of the features of Fred within it. This is available in every single version of Fred. So any of you that already have Fred or are looking at Fred, everything you've seen here today will be possible in the version of Fred that you'll have. Okay, thanks for coming. Hope to have another webinar for you in, I don't know, maybe September time after the summer break. If any of you have any topics you'd like us to discuss on a webinar like this, then let us know as well. We're always happy to hear about what you guys are interested in. But other than that, I hope you have a lovely summer, and we'll see you for a webinar in future. Thanks a lot.